All right, everyone. Hello. Welcome to chapter 11, lecture number 3. We'll finish up the chapter here. So let's continue with the slides to our third theory, third and last theory of the chapter. We just went over valence bond theory, right? So you guys learned about which orbitals overlap in order to form the bond. But there are limitations, right, to each theory. And the limitations of valence bond theory is that um, it presumes that electrons are still localized in orbitals, and it doesn't really account for delocalization. Um, so there are still many things that it's unable to predict, such as magnetic behavior. Um, and so that's why we bring in this third theory, just called molecular orbital theory. Okay, so we have, right, all these theories so far, and they're still gonna be in play, right? It's just that we're bringing in another theory to describe other things that these previous theories, just approximate uh, or they lack, right? So Lewis theory tells us, um, how to draw molecules, and gives us like a first approximation, right, of bond angles. But it's really the Sieper theory that describes molecular shape and really gives us more accurate bond angles. And then valence bond theory described the bonding in terms of orbital overlap. And that's actually more, true to real life, right? Because the orbital overlap is quantum mechanical. It's from a quantum mechanical basis. But MO theory is now going to be able to tell us about magnetic and spectral properties of molecules. And the main idea is that the atomic orbitals are wave functions, right? As we know from quantum mechanics. And that's where the atom's electrons are, okay? But now when atoms come together to make a bond, then basically the atomic orbitals um, that are on each atom, they mix again. And by mixing, we mean like constructive interference and destructive interference to form what are called molecular orbitals, right? And these are the orbitals in molecules, right? Um, and this is where the molecule's electrons are going to occupy. Right? Okay, so we can start really simple, right? With just two hydrogen atoms. So when two hydrogen atoms start to come together, their atomic orbitals will overlap. And by overlapping, what we mean is it's a um, constructive and destructive interference, right? So that's the two ways, right? If the wave functions are added, that is called constructive interference, and we will get what's called a bonding MO. MO standing for molecular orbital. And a bonding MO is defined as the region of space of high electron density between the two nuclei. Okay. So think of bonding MOs as a good thing, right? For bonding. Okay. Now, the other way that it can interact is subtraction or deconstructive interference, right? Which you guys know. And when deconstructive interference happens between the atomic orbitals, we form what is called anti-bonding MO. And that's where you have a note, right? A region of zero probability of finding the electrons of the molecule. Okay. So we really have established the boundaries here, right? The bonding MO where we have constructive, it's where it's constructive for bonding, right? And then we have anti-bonding MO, which is no bonding. Okay. So that's, we can think of these atomic wave functions colliding or mixing, adding and subtracting, just like light, right? And we know that light waves, they interact also constructively and destructively. So in a bonding MO, the atomic orbitals will be in phase, right? And so the amplitudes of uh, the wave will add here, right? So the wave function's the same. It will also add. But if the amplitudes of the wave functions are interfering peak to trough, then they're going to be canceled out. And so that's what we have, anti-bonding molecular orbitals, right? So one is good, and one is bad to bonding. Okay, that's how you can think of it. And those are the boundaries. Right? Okay, so back to our two hydrogen atoms, right? Here they are, and you can see their electron cloud, right? Remember, hydrogen is 1s1. So the 1s orbital is a spherical shape, right? And when they constructively interfere, or when they add, right, what you get is the bonding MO. And look at what the bonding MO looks like now after these add together is you have this region of space in between the nuclei where you have um, a probability of finding the molecule's electrons, right? When you subtract, look at the picture here. There's nothing, right? Nothing in between the two nuclei. So that's why it's called an anti-bonding. It's not constructive to bonding, this orbital here, okay? So it's only the addition that is going to be good to bonding. And these MOs, right, these molecular orbitals are now called based on what the atomic orbitals that made them are. So for example, because the 1s and 1s collided, to make this bonding MO, it's called the sigma 1s. Okay. So why sigma? Sigma starts with the letter S, and so it's because the s orbitals are um constructively interfering, right? So that's how I remember it. Sigma S, right? And so the sigma 1s, so the subscript here 1s tells you it's the 1s orbitals that made this MO. And then this anti-bonding MO carries almost the same label, sigma 1s, but it has an asterisk by it, and we call that a sigma 1s star. A sigma 1s star, anything with the star is an anti-bonding molecular orbital. Okay, so that's how we denote an anti-bonding from a bonding. Okay, but it's still made, right, by colliding two 1s orbitals, and so that's why it still is called a sigma 1s. Okay. So now let's talk about the potential energy of the two. Notice that the bonding molecular orbital lies lower in potential energy than the anti-bonding molecular orbital. That's not surprising, right? Because when you have an addition, you lower the energy, okay, of the molecular orbital. When you have a subtraction, you will destabilize it. So the anti-bonding MO will always be higher in energy than the bonding MO. Okay. So now if we were to construct an MO diagram for H2, this is what it would look like. First, draw your arrow pointing up and we'll label that energy. So meaning energy is increasing in the up direction. Okay. Then you start with the orbital diagram. See, this is why we teach you orbital diagram, right? Not just electron configuration, or orbital diagram, because we've been using orbital diagram now in two of the theories. So make sure you know how to do your orbital diagram. So for hydrogen, easy. 1s has one box and one electron in it, right? So this is, we can label as the atomic orbital, AO, the atomic orbital of H, right? Well, the other atom is another H as well. So it also has 1s1, okay, and labeled atomic orbital of H, okay? So these are already existing atomic orbitals. Now imagine what happens when they come together and these two 1s do constructive interference and destructive. And in the middle column is where you show that. So with constructive interference, we get this box, okay? And we're going to label it sigma 1s. Why? Because a sigma, it's a sigma bond, right? A 1s and a 1s orbital will collide to make a sigma bond. And this is something we already learned when we learned valence bond theory, right? Remember that? Head-to-head bond is sigma. So it'll be a sigma 1s for this box. And you also have another box, but it lies higher in energy, right? So you destabilize it. So not only is it higher in energy than the bonding molecular orbital, but it's also higher in energy than the starting atomic orbitals, right? Because you have a destabilization of this orbital. That's why it's called anti-bonding. So it's called sigma 1s star. That's your anti-bonding, okay? So this middle column is called the MO diagram, right? The molecular orbital diagram. And these are called the molecular orbitals, okay? The middle column, all these boxes are called the molecular orbital of H2. Okay, so in the middle column, what you do last is you place the number of total valence electrons into that column. So just like how you do for Lewis structure, what is the total number of electrons for H2? 2, right? 2 times 1 is 2. So you place 2 electrons in the middle column. And you do it just like how you fill out orbital diagram. Aufbau principle, so lowest energy orbital first to highest. Pauli exclusion principle, when it's in the same box, you got to have opposite spins. And then Hund's rule. Remember Hund's rule? Don't be the creep person on the bus. So 1 in each box first before you pair it, okay? So with 2 electrons, it's obviously you're going to start at the bottom box, top, spin up, and then spin down, and you're done. Okay, so that is the molecular orbital diagram for hydrogen. Okay, pretty simple, right? Now, to get the bond order, what you do is you take the number of bonding electrons, the good electrons, that's how I think of it, and then I subtract the bad electrons, right? And divide by 2. Right? So it makes sense that that's the bond order because remember the MO, the bonding MO is conducive to bonding, right? Whereas the anti-bonding MO is not conducive to bonding. So that's why you take the difference of the 2 electrons types. And then why divide by 2? Because every 2 electrons is 1 bond, and you're trying to find the bond order. Okay, does that make sense? So here it goes. The number of electrons in bonding is 2, right? Subtract the number of electrons in an anti-bonding orbital, none. There's none in this picture, right? So 2 minus 0, divide by 2. 4 times 1/2 is equal to 1. So the MO diagram or molecular orbital theory has correctly predicted that there should be a single bond between H2. And we know that to be the case, right? And that matches Lewis theory. It matches valence bond theory, right? When you draw H2 Lewis structure, you see a single bond as well, right? When you do valence bond, or when you do the bonding scheme of H2, you also see a single bond, right? So that's how that works, okay? Again, take the number of good electrons, subtract the number of bad electrons, right? That's easy to remember. Divide by 2, and that's how you get your bond order, okay? Now, interpreting that bond order, this bond order is no different than the bond order when you do your resonance hybrid, right? Remember that, we know that. It tells you the strength of the bond. Of course, the higher the bond order, the stronger the bond's going to be, okay? But what does that mean if in MO theory, if your bond order is a positive number, like it's greater than 0, that means that the molecule is more stable than the separate atoms, and therefore it will form, right? So what MO is able to tell you is whether the molecule can exist or not, right? Whether it's existing right now, we don't know, right? Maybe, some chemists haven't made it yet, right? But MO can tell you whether it can be made, right? So that's the powerful thing about these theories, right? Because you don't want your chemists to be wasting time. You don't want your experimentalists to be wasting their time trying to make a molecule that's not gonna theoretically be able to exist, right? And so that's what MO theory in a way does for these chemists, is to tell us, can we even should we even try, right, to make some molecules? Okay, so again, if your bond order is 0, the molecule will not form. It does not exist, right? And if it's a non-zero number, then theoretically it could exist, right? Could try and make it, right? Okay, so let's do the MO diagram for these 2. I'm going to switch to the board just because it's going to be easier. And I can show you guys how you should do it on paper. So we're going to do He2 cation and He2. And then it asks us if these two exist, right? So we will do the bond order, and then we will see whether they exist or not. Okay. All right, so remember how we do MO diagram. We start off first with the atomic orbitals of each of the atom. So AKA the orbital diagram. Okay, let's do He2 cation first. So think about what two atoms go into making He2 cation. One of them has to be He, okay? And the other one has to be He plus. Doesn't that make sense? Because now when you put these two together, that's He2 cation. Okay. Now that's some people get confused, and I'll just tell you off the bat. So hopefully you don't do this. Some people have gotten confused and they think it's He plus and He plus. That's not right, because if it's He plus and He plus, that should come together to be He2 2 plus. And that's not what we're talking about, right? Because that's a 1 plus, that's a 2 plus. So we are only talking about He2 single cation. So that is going to be a helium neutral and a helium plus. Okay. So now we draw the orbital diagram of helium neutral. This box. It's 1s2, right? Okay. And then He cation is He missing an electron. So He is normally 2 electrons. Now it's missing one, it just has one inside. Okay. So these are the atomic orbitals. You can say these are the AOs, He plus atomic orbitals. Here are the helium atomic orbitals. And now in the middle, we're going to make them collide, right? One's going to be constructive interference, which means we will get a bonding molecular orbital. This is 1s, right? So 1s is colliding. This one's going to be called sigma 1s. Okay. And then we'll get an anti-bonding as well, which is higher in energy, right? Energy going this way. We'll call this one what? Sigma 1s star, right? Because it comes from the 1s and it's an anti-bonding. Okay. So in this middle column, this is our MO, our molecular orbital, right? Showing the results of what happens when they add and when they subtract, right? That's what these dotted lines, right? Okay, so now the last thing we do is we put the electrons into the middle column. The total number of electrons for the entire structure, He2 cation, count it just like you would when you do Lewis structure. That's 2 times 2, but with the cation, it's a -1, right? It's of the plus charge. So that's 3 valence electrons total. So that's where you put 3, but you can also look at here, right? That's 3. So 1, 2, and 3, right? The third one has to go into the antibonding orbital, right? Because this is already filled. Remember, 2 electrons per orbital. Okay, so now we do a bond order, right? So bond order, remember how we count? Good electrons minus bad electrons, right? So bonding electrons, count all of them. You total up all of them, and then total up all of the bad electrons. Take the difference and then divide by 2. So that's gonna be 2 minus 1 over 2. And that's 1/2. Okay. So we have a bond order of 1/2. So He2 cation can exist. Right, it does exist. Okay. Let's do He2 and compare. So again, we have to figure out what 2 atoms make up He2. Obviously, it's going to be He and He, right? And He is 1s2. The other He is also 1s2. Okay, let's make them collide. We call this the sigma 1s. This one's a sigma 1s star, right? The bonding and the antibonding. And then we fill in the total number of valence electrons for He2. That's 2 times 2 is equal to 4, right? And we can see the 4 here too, okay? So 1, 2, 3, 4. Okay, now we do the bond order. Bad electrons, or good electrons first, sorry. Good minus bad. So 2 electrons in the bonding minus 2 electrons in the antibonding divided by 2 is equal to 0. Okay, so does He2 exist? No, it doesn't. So write D and E does not exist. Okay, so He2 does not exist. This isn't surprising, right? We already know this. We know that noble gases do not like to bond, right? So He does not want to bond with itself, right? So molecular orbital theory is telling us that, right? Something that we kind of guess already, right? We're kind of new. So it's congruent with all the other theories, right? So this is, again, what you're drawing here. First, start with the atomic orbitals, right? And then make them collide. And your middle column is your MO diagram. Right? So as you can see in the first period, we've done hydrogen and now we've done helium. In the first period, we have this shape, right? Like this baseball diamond here. We will see that in period 2, it's gonna look a little different. So let's go back to our slides here. Okay. Oh, one more thing as well. If you are asked to write the electron configuration for the MO diagram, just note what is, how many electrons are in each MO, in each molecular orbital. So for this first one, you write, okay, there are 2 electrons in sigma 1s. So sigma 1s 2, and then there's 1 electron in sigma 1s star. So you write sigma 1s star superscript 1, right? It's pretty much like doing a regular electron configuration where you're like 1s2, 2s2, 2p6, right? But here you're doing it with molecular orbital. So you go sigma 1s2, sigma 1s star 1. Okay. In the helium He2 case, it'd be sigma 1s2, sigma 1s star 2. Okay, let's do this one together as well. Use MO diagram to predict whether H2 cation and H2 anion exists. Determine their bond orders and electron configuration. So we got H2 cation versus H2 anion. Okay. So again, starting with atomic orbitals, right? Let's do H2 cation first. What 2 atoms come together to make H2 cation? H and H plus, right? So we do 1s for H, and for H plus, we do 1s, but don't put any electrons in it, right? Because it's missing its electron. Then we make it collide. This would be called sigma 1s. On top, the antibonding is called sigma 1s star. Okay. And then how many electrons do we put? So this is the atomic orbital, or on the sides, and then in the middle, this is our MO. So in our MO column, how many electrons are we going to put? Well, the total number of electrons of H2 cation is just 1, so we just put 1. Okay. When we do bond order, then easy. Good electron minus bad electron divided by 2. So 1 minus 0 divided by 2 is 1/2. Okay. So we can say that H2 cation can exist. Okay. Let's do H2 anion. So again, we ask ourselves, what two atoms make up H2 negative? Well, it's got to be an H, and the other one has to be H negative. Okay. So here's the atomic orbitals of each of the hydrogen, right? It's 1s1. For H minus, it's 1s2, right? This hydrogen normally has one, the negative sign means it has an extra. Okay, so that's what we got. And then we make them collide. This is called the sigma 1s. This is called the sigma 1s star. Okay, and then we put how many electrons in the middle column? 3, right? So we're gonna do up, down, up. Right, the third one has to go into the antibonding orbital. Okay, and then we say what the bond order is. Good, the number of good electrons is 2, minus the number of bad electrons, 1. And we divide it by 2, so we get 1/2. All right, so H2 negative can exist as well. Right. And which one is, and they're both at the same strength, it looks like, right? Because they have the same bond order. Okay. So, H2, remember when we did H2 neutral, it was a single bond, right? And then H2 cation, H2 anion is both half of for their bond order. So obviously H2 neutral is more stable because it has a higher bond order. Okay. The bond is not even equal to 1, right? It's not even considered a single bond. It's less than a single bond, but it's non-zero. So at least it can exist, right? It would just be very unstable. Okay, let's go back to our slides. And we're gonna go to period 2 now, right? We just did hydrogen and helium. We go to lithium and beryllium. So we'll do Li2 first, right? Start with the atomic orbitals of lithium, right? Li2 is comprised of a lithium and a lithium. So each lithium is 2s1, okay? So again, we have our baseball diamond, but now they're called different, right? Because the bonding orbital, the bonding MO is now called sigma 2s, right? Because when s orbitals collide, it's still a sigma type bond, right? But now it's from which orbitals? It's from the 2s. So now it's sigma 2s. And we put 2 electrons in there because Li2 has total number of 2 electrons up and down. Then when we do bond order, it's going to be 2, right? The good electrons. 2 minus 0 is 2, divided by 2 is 1. So theoretically, Li2 can exist, right? And it will have a bond order of 1. That's what MO theory predicts. Then BE2, each BE is 2s2, okay? So it's going to get the same pattern. It just has a different number of electrons in the middle. Still the same MOs, right? Sigma 2s and sigma 2s star. It just has now 4 electrons in there. So when it has 4 electrons, everybody's filled, right? And so you have the same number of electrons in bonding as you do in anti-bonding. So of course your bond order is going to be 0, right? Because it's going to be bonding minus anti-bonding divided by 2, right? Okay, so does BE2 exist, everyone? No, it does not. Okay, now let's move on. We just did lithium, we did beryllium. Let's move on to boron, okay? Now, when we're at boron, we are in the P block, right? Because boron's configuration is now 2s2, 2p1, okay? So the p orbitals now are also going to do constructive interference and destructive interference. So let's take a look at what those look like, because so far we only looked at the s. So the p look like the peanuts, right? So if you got two px orbital, for example, mixing, when they constructively interfere, you see this bulbous region in between the two nuclei. That's conducive to bonding, right? And that's why that orbital is lower, right? You have a stabilization of that. And so this is called the MO, the bonding MO, and it's labeled as sigma 2p. Okay, well, why? This type of overlap, right, is sigma, okay? And what orbital is it coming from? The p orbital, so sigma 2p, right? Now, when they subtract each other, or aka destructively interfere, you see that there is a node in between the two nuclei. So this is not conducive to bonding, therefore it's called the anti-bonding MO. And the label is sigma 2p star, right? So again, sigma because of this type of bonding, 2p because it's coming from the 2p orbitals. Okay. All right. Now let's go to the py. Okay. So in the first p orbitals will always do sigma. You guys remember that from valence bond theory? When you have multiple bond, there's always one sigma bond and the rest are pi bonds. So now when you go to the py, they're going to do pi bonding. Okay, so they'll do the side-to-side overlap. And when they constructively interfere, you'll see the label is pi 2p. Okay, and then pi 2p star for the anti-bonding. Okay. And you have PZ doing that as well, right? So in the end, what you have is 6 molecular orbitals when the p orbitals mix. And this is the order that they would typically be in. The sigma 2p is going to be lowest in energy. And so therefore its anti-bonding sigma 2p star is going to be the highest, because what we're doing is we're establishing that the boundaries there, right? So the more stable the bonding MO is, the more unstable the anti-bonding is. Okay. And why is it that sigma is more stable? It's lower energy than pi, because we saw that, right? Sigma overlap is bigger than pi overlap. So it's a stronger bond. And so that's why it's more stable. Okay. But that also means that its anti-bonding is even more destable. So it forms the boundaries, right? So those are the tops. And then in between is where you have your pi 2p and pi 2p star. So in the end, what you get is two let's look at the left picture first. What you get in the end is these 6 molecular orbitals. Okay, you guys see that, right? Because it's conservation of energy, right? 3 and 3 makes 6. Okay, so the px is going to form the sigma 2p star. And then when the py come together, they form pi 2p and the pz as well. So the pi 2p is going to be 2 boxes, right? Because that's due to the constructive interference of the pz and the py together. And then up top here, you have your anti-bonding. These 2 pi are coming from the destructive interference of py and pz. And then this one, the highest orbital, sigma 2p star, is from the destructive interference of the px. Okay. So the way I remember this pattern is 1, 2, 2, 1. It's very symmetrical. Okay. And this pattern right here is going to be for oxygen, fluorine, and neon. Right. What we're seeing is there's no 2s 2p mixing. So what does that mean? Well, let's go down here. We're familiar with this baseball diamond, right? We've seen it before. So you have the 2s mixing, and you get sigma 2s here and sigma 2s star here. Okay. What does it mean without 2s 2p mixing? Is that the 2s is not going to mix with the 2p. Because they're too far apart to mix. Okay. Now, let's go to the other pattern. For boron, carbon, and nitrogen, you do have 2s2p mixing. So what happens is it kind of screws up your very symmetrical looking MO diagram here. It makes the sigma 2p be higher than the pi 2p. Okay. So now you have a 1-2-1-2 pattern. This is only for boron, carbon, and nitrogen. Okay. So that's the result if 2s and 2p orbitals are close enough to mix, then when they do, the sigma 2p will be higher than the pi 2p. Okay. And we can actually explain this. So let's go to the board and see why there's mixing for boron, carbon, and nitrogen, and why there's no mixing for oxygen, fluorine, and neon. Let's look at oxygen first. That's 2s2, 2p4, right? When you look at nitrogen, it's 2s2, 2p3. Okay, so for nitrogen, there's mixing. For oxygen, there's no mixing. And what type of mixing? 2s2p mixing. Okay, so nitrogen has 2s2p mixing because the energy gap between 2s and 2p is smaller than in oxygen. Why is that? Well, in oxygen, all of a sudden you have more electron-electron repulsion, right? Because in nitrogen you had 2p3 and there was no crowding, right? Then you add another electron in oxygen and all of a sudden you have this electron-electron repulsion. What that does is it drives the 2s further apart from the 2p, okay? So since this gap is large, no mixing. Okay, so this is the case for oxygen, right? But in nitrogen, since you have 2p3, okay, no electron-electron repulsion. So now this energy gap is small. And so you do have 2s2p. Okay. So all I've provided to you guys is a reason why you have 2s2p mixing in nitrogen and carbon and boron. It's all the same because for carbon it's 2p2, right? So you still have no electron-electron repulsion. And then for boron it's 2p1, okay? For oxygen, fluorine, and neon, you have no mixing because this is so large due to the increased electron-electron density, the electron-electron repulsion, right? So in fluorine, you'll be 2p5, and so you add another electron here, even more electron-electron repulsion. Okay? Okay, so that's the reasoning, but really you guys don't have to really worry about that. Just remember the pattern. Okay, so for oxygen, fluorine, neon, it keeps the very symmetrical 1-2-2-1 pattern for the p orbitals. Okay, and then for boron, carbon, and nitrogen is 1-2-1-2, where the sigma 2p is just above the pi 2p. The rest are the same, right? Okay, so now this is how we're gonna do the rest of period 2. So let's do B2. B2 neutral, right, is how many valence electrons total? 2 times 3 is 6, okay? And for boron, remember, there is mixing. So it's 1, 2, 1, 2, okay? And then this is 1, 1 from the 2s, right? So 6, 1, 2, 3, 4, 5, 6. The bond order is, count up all the bonding electrons, 2 from the sigma 2s, 2 more from pi 2p, so that's a total of 4. 4 minus 2, because that's an antibonding, is 2. 2 divided by 2 is 1. So there's your bond order for B2. For C2, again, you still have mixing, right? So the pattern is still 1, 2, 1, 2. C2, you have a 6 valence electrons total, right? 2 carbons. So you're going to fill it 1, 2, 3, 4, 5, 6. Sorry, it's 8 valence electrons total. So you're going to do 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now to do the bond order, count all the bonding electrons. So that's 2 from the sigma 2s, 4 in the 5-2p for a total of 6, and minus 2 for the anti-bonding sigma 2s star. So that's 4. 4 divided by 2 is 2. Okay, so it's predicting that C2 will have a double bond. And then let's do N2. N2 total number of valence electron is 5 times 2, which is 10. It has mixing, so remember it's 1, 2, 1, 2. So let's fill in 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now for the bond order, you're going to do the bonding electrons. That's 2. Plus another 4 here in the pi 2p. That's 6. And then another 2 in the sigma 2p. So that's 8. Then you subtract 2 from the antibonding sigma 2s star. That's 8 minus 2 is 6. 6 divided by 2 is 3. Okay, so it predicts that N2 should have a triple bond. This is congruent with Lewis theory, right? So if you draw N2, you'll see that it has a triple bond, right? The Lewis structure of N2. And it predicts that it's diamagnetic, right? C2 should be diamagnetic as well, and B2 should be paramagnetic. Right? All right, let's go to O2 now. Remember, when we cross over to oxygen, we don't have mixing anymore, so it goes to the pattern of 1, 2, 2, 1. Okay. So O2 has 12 valence electrons total, right? So that's how you fill it. Now the bond order, let's count. Bonding electrons, 2, 4, plus another 4 here is 8. Subtract the bad electrons, that's 2 here, another 2 here is 4. So 8 minus 4 is 4, divided by 2 is 2. Great, it predicts that O2 has a double bond, right? So when you draw the Lewis structure of O2, it also has a double bond, right? But interestingly, what does it predict for O2 as the magnetic properties? It predicts paramagnetic. The other two theories were unable to do that. Valence bond theory predicted that O2 was diamagnetic. Lewis theory was saying that it was diamagnetic, right? So it's only molecular orbital theory that was able to tell us that O2 is paramagnetic. Okay. When we go to F2, right, we have 14 electrons now. Bond order is going to be 1. And then what does it predict for neon 2, Ne2? Should be 0, right? So noble gas doesn't want to bond. Well, that makes sense because all of the orbitals are filled up. So the number of good electrons are the same as the number of bad electrons. So good minus bad is 0, right? So it's not going to exist, Ne2, okay? All right, so we did this problem already. Let's do this problem. Draw the MO energy diagram and determine the bond order for the N2 negative ion. And you expect N2 negative to be stronger or weaker than N2. And then it's asking if it's diamagnetic or paramagnetic. Okay, so we basically, well, let's just do both N2 and N2 minus. So we can compare. Okay, let's do N2 first. So the two atoms that go into making N2 is N and N. And we're going to come up with the molecular orbital diagram of N2. Okay, so we start with the atomic orbitals of N. It's going to be 2s2 2p8, right? And then same here for this N. 2s2, 2p. All right, so the 2s is going to come together constructively to make this bonding MO, and we'll call that the sigma 2s, right? And then it's going to destructively interfere to make this sigma 2s star. Okay. And then for the 2p, remember, where's nitrogen? Nitrogen has mixing, right? So that means we're going to have the pattern of 1, 2, 1, 2. Okay. So 1, 2, 1, 2. Okay. And then make sure you label it. The set of double is always the pi, okay? And pi 2p. And then just the 1 is sigma 2p. The one that's upper is going to be pi 2p star. And this one is sigma 2p star, okay? So for mixing, for the ones that can mix, so boron, carbon, and nitrogen, it will always be this pattern, everybody, right? So there's only 2 patterns you got to memorize, okay? That's it. Then go ahead and draw the dotted lines here to show interference, right? Constructive and destructive. And then now you fill in the total number of valence electrons for N2. That's 2 times 5, which is 10. So you gotta go 1, 2, 3, 4. And then here's Hund's rule. Watch this. 5, 6, 7, 8, 9, 10. Like that, right? Okay, now we count for bond order. The number of bonding electrons. So 2. Here's bond 4, 6, 8. And then we subtract the anti-bonding electrons. All the electrons are in star orbitals, so notice that's only 2. And then we divide by 2. 8 minus 2 divided by 2 is 3. So we are predicting a triple bond for N2, right? Using molecular orbital theory. And as you can see, that is absolutely congruent with Lewis structure. That's the structure of N2, right? Triple bond. All right, let's do N2 negative and see how it compares. So what are the 2 atoms that make up N2 negative? What's going to be N and negative, obviously, right? So here are the atomic orbitals. Yeah. 2s, we got the 2p, 2s2, 2p3 for N. And for N minus is 2s2. Right? 2p3 is normally, but then you have an extra electron, so put an extra electron in there. It's going to be 2p4. Okay. All right, and then you make it mix. Here's my sigma 2s. Here's my sigma 2s star. And then nitrogen again, the pattern is 1, 2, 1, 2. I'll just generate that first. 1, 2. One, 2. And we'll label it pi 2p, sigma 2p, pi 2p star, sigma 2p star. Okay. The number of electrons that we put in there, well, total number of valence electrons, 2 times 5. The negative charge is +1. Okay. So that's going to be 11 valence electrons. And we're going to do 1, 2, 3, 4. Watch Hund's rule here. 5, 6, 7, 8, 9, 10, and then 11. I gotta go there. Okay. So now I have another electron. Okay, so bond order. So this is the MO, right? The middle column. Bond order. Count the number of good electrons. 2 4, 6, 8. And then subtract the number of bad electrons, the one in the anti-bonding orbitals, 2 and 3. So 8 minus 3 over 2 is 5/2. Or you can say 2.5. Right. So what has happened from N2 to N2 minus? That's what the question was asking us, right? In N2 minus, we've weakened it, right? N2 minus is less stable than N2. Okay. They both exist, but N2 minus has a weaker bond order, right? It only has a bond order of 2.5, whereas N2 was a triple bond. Right? And then it also asks us to list whether it's diamagnetic or paramagnetic. So here, when the electrons are paired up, we call this diamagnetic. Here we have one unpaired electron, so this one is paramagnetic. Remember how that goes? If you have at least one unpaired electron, you're paramagnetic. Only if you're completely paired up, you're called diamagnetic. All right, let's go back to the slides. All right, let's see if we can do one more example for you. Yeah, let's do one for O2 and O2 minus, right? We'll kind of do the same comparison here, except with oxygen. Okay, so for valence electrons, 2 times 6 is equal to 12. 2 times 6, that negative charge means a +1. So 13 valence electrons. Okay, we're gonna need those later, right? Now we ask ourselves, what two atoms make up O2? It's gonna be oxygen and oxygen. And atomic orbitals. You have a 2s2, two p4, and the other oxygen is the same, 2s2, 1, 2, 3, 4. Okay. All right, let's do the S first. It's going to be the base bond diamond that we already know, right? Constructive interference will give us a sigma 2s. Destructive interference will give us a sigma 2s star. And this is our MO diagram in the middle. Okay. And then remember oxygen, fluorine, and neon, no mixing. So you get that nice symmetrical pattern of 1, 2, 2, 1, 1, 2, 2, 1. Okay. Notice how that was different than our last example because there it was nitrogen. Okay, so you gotta just remember that. Again, B, C, and N, 1, 2, 1, 2. O, F, and N, E, 1, 2, 2, 1. Okay, that's all. There's no other one, just those two. Once you have that, right, connect this. Put the electrons in. We said 12 electrons. Put it in to this MO diagram. Start at the bottom. 1, 2, 3, 4, 5, 6. Watch Hunt's rule here. 7, 8, 9, 10, 11. Hunt's rule again. 12. Put it in the other box first. Okay. Also label your MOs. The single box is always a sigma. Okay. And it's at the bottom, so it's just 2p, right? This one is pi 2p. The double box is always pi. And since this is above, it's pi 2p star. This one's highest in energy, so it's 2 sigma 2p star. Okay. Now we do the bond order. Good electrons, 2, 4, 6, 8. The bad electrons are the ones in the antibond. 2, 3, 4. Minus 4 over 2 is 2. Okay. So, molecular orbital theory predicts that O2 will have a double bond. Indeed, it does when you draw the Lewis structure, right? 2, 4, 6, 8, 10, 12. Okay, so it matches. Let's see what it would be for O2 negative. So what are the two atoms that make up O2 negative? Well, obviously O and O negative. So let's do the atomic orbitals first. It's going to be 2s2, 2p4, for O minus, 2s2, 2p, right? O normally has 2p4, but with a negative, it has another one. So it's going to be 2p5, right? So add another electron in there. Okay, then you make it mix. This is the sigma 2s. This is the sigma 2s star. And then remember oxygen, the pattern is 1, 2, 2, 1. 1, 2, 2, 1, like that, right? And this is the sigma 2p. This is the pi 2p. This is the pi 2p star. This is the sigma 2p star. You must label all of the MO, right? All of the molecular orbitals. Now you fill in the electrons, 13. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Right? What is the bond order? Good electrons, 2, 4, 6, 8. Minus the bad electrons, 2 and a 3, 2, 4, 5. So 5. From 8 is 3 divided by 2, 1.5, 3 halves, right? Yep. So let's compare it to O2. What happened? Again, you'd have a decrease in bond order. So O2 minus is less stable than O2. Okay. Interesting. It kind of mirrors what nitrogen did, right? So by adding an electron into an O2 neutral, it weakens that double bond, right? From a bond order of 2 to 1.5. And with nitrogen, it was similar, right? It went from triple to 2.5. So it actually weakens it. Okay. Now, this is really cool because MO theory basically is telling us that if we pump electrons into these very stable triple and double bonds, we can weaken it. And why is that significant? Well, if you have triple, you have a really, let's say, a pollutant in the atmosphere, like CO2, right? It's a greenhouse gas. Because CO2 has double bonds, right? What MO theory tells us is if we put electrons in there, because that's what we did here, right? Put an extra electron in there. If we put electrons in there, it will weaken these bonds. And then we can eventually break them and turn CO2 into something else. So we're basically taking CO2 out of the atmosphere that there's too much of, and we turn it into something more useful. Okay. And it's because of MO theory that all these research positions out there, all these research groups is studying this, right? They are pumping electrons into very stable molecules to try and weaken them and turn it into something else. There are a lot of scientists, lots of chemists trying to break this triple bond, right? Because nitrogen makes up 70% of our atmosphere. We don't need it to breathe, right? What if we can just take some of it and turn it into ammonia, which is a feedstock, which is a very important industrial molecule, okay? That is very expensive to make right now, okay? We're doing it through another process, but it's costing us a lot of money. So ammonia is basically like fertilizer, right? So very important feedstock. But now, right now, it's very expensive for us to make, right? So there's a bunch of groups. And when I was a PhD student, that's how I got my doctorate was I was taking uranium, okay, and pumping electrons into CO2, into N2, into a bunch of other small molecules to try and turn it into something more useful. And that was all due to, knowing what we know from MO theory, right? Now, this is very simple, right? All we did is just to up to period 2 elements. And by the way, that's all you guys have to know. You do not have to go past period 2. So I will only ask questions up to neon, okay? And so you guys should be able to do it all, right? Um, but it's very simple, right? We're only also just doing diatomic, okay? MO theory can get very complex once you have bigger molecules, and we can no longer do it on the board like we've been doing. We need computers in order to do that, right? But it will use the basis of MO theory to tell us basically, how what kind of orbitals are in these molecules, what would happen if you put electrons in there, um, you know, um, of very useful information, right? That will guide the research that we try to do. Okay, so back to our slides here. So O2, right? That's one of the advantages of MO theory, molecular orbital theory, is that it's able to predict magnetic properties, whereas valence bond theory, Lewis theory couldn't do it. So O2 dioxygen is paramagnetic. We know that for a fact. But it's only molecular orbital theory that actually predicts that. Okay, so we've been just doing diatomic, and not just diatomic, but homonuclear, meaning the same atoms, right? Once we get to diatomic, the MO diagram looks really complex already, right? So let's say if we do an NO molecule, so you can see that now the energy levels have shifted, right? It's very asymmetrical because the nitrogen is not the same as the oxygen. So the gap between the 2s and the 2p is different. So um, the molecular orbitals start to get a little bit more complex. But just now imagine, an actual molecule, let's say 6, 7, 10, 20 now atoms, right? How the molecular orbital would look. And so that's why we need a computer in order to do that, right? We can't do that on the board anymore. Okay, so you guys don't have to do heteronuclear, just do homonuclear like I've been showing you guys, and all you have to know is up until neon, right? So it's all there for you guys right here, right? So I'm only gonna ask basically up to neon. Of course, I can ask about Ne2 negative or Ne2 positive, right? I can ask, say, F2 plus, and you should be able to do that, okay? But yeah, I'm not going to ask you about any other elements past period 2. Okay, guys, so that's it. That's it for chapter 11. Okay. I will see you guys next time for chapter 12.